Okay, so welcome to Complex Analysis, Math 383. This is lecture, I think, 32. And I want to continue with, connections, with number theory and random matrix theory. So it doesn't look like it is sharing the screen. So let me try again. Okay, so what I want to do is I want to talk about how we can actually use complex analysis to talk about solutions to problems we care about. And so some of you who have done work with me could probably give this lecture yourself. If you ever feel like I'm not doing a good job, by all means, feel free to rush the stage and take over. You might even recognize some of the slides. So we talked a little bit about random matrix theory, where you choose a matrix, and depending on the problem, that matrix will have different structures, and you want to calculate properties of the eigenvalues. Well, it's very hard to get at the eigenvalues of a matrix, but if you're choosing the elements of the matrix from some distribution, you know things about the matrix elements. And so we have formulas that allow us to pass from knowledge of the matrix elements to knowledge of the eigenvalues and vice versa. We care about the direction going from matrix elements to eigenvalues. The subject began by looking at matrices with the entries drawn independently from distributions. But nowadays, number theorists don't use this model anymore. They actually use the classical compact groups, they use unitary matrices, they use Haar measure. And the reason is that's the natural way of choosing things. Out of curiosity, how many people have seen Haar measure and the classical compact groups who have not worked with me? Okay, so I'm not going to go into much detail about that, but just saying that there are ways to put probabilities on spaces of matrices so that you have nice properties. And if you look at the Lebesgue measure, if you look at what's going on the real line, you have a translation invariant measure. If I replace variables with x plus a, it doesn't change the dx. When we did Stirling's formula, we looked at dx over x. That was invariant under rescaling by a multiplicative factor. Dx over x is the same if I replace x with constant times x. You can do the same with spaces of matrices. And if you have a compact space of matrices, if you look at unitary matrices, well, unitary matrices, UHU equals the identity, or the real analog, Q transpose Q is the identity. Basically, each row has length 1. So there's a compact set that things live in, and you can then talk about putting a probability distribution on such a space of matrices. Because it's compact, things are very nice, and you can create a measure that is invariant under translation by matrix elements. So there's a lot of really nice group theory that's lurking in the background that we're not going to get to. And what we want to do is we want to analyze sums that look like this. And so we talked a little bit about last time that we look at the expected values. So we're averaging over all the matrices. So we weight each matrix by the probability it occurs. And if any of the aij's is unmatched, since we're assuming our elements have mean 0 and variance 1, if it's unmatched, that just gives us 0. So everything is matched in at least pairs. It could be matched in triples or quadruples. And then that's where you look at, we're dividing by n to the k halves plus 2. And so if you look at how many different pairs we have, well, we have k variables. So we have an n to the k. So we have n to the k tuples. That's a lot more than n to the k halves plus 1. But since everything has to be matched in at least pairs, you lose a lot of degrees of freedom. And so the number of tuples that can actually contribute, if you ever had a triple or quadruple matching, if you just go through and do the calculation, it turns out it's a lower order term. When you divide by n to the k halves plus 1, it just goes to 0. And again, the goal is for you not to understand every line of the calculation, but to just get a sense of the types of problems that can be studied and how complex analysis and other mathematics can enter into problems like this. So if you, as I've remarked, are not going to be graduating this year and you're interested in looking at problems like this over the summer, let me know because I will be running small again. And it would be nice to have students who've actually done complex analysis and don't have to learn complex analysis in 1 hour, as had to be done a couple of years ago. All right, so the ensemble we talked about at the very end of the last class was the block circulant matrices. And so these matrices are constant along wrapped diagonals up to some kind of periodic repeating. So here I've got an example that's period 2, so it goes C2, D2, C2, D2, C2, D2, and then wraps around to C2, D2. It's always interesting to try to figure out what exactly is the right object to study. Years ago, I was looking at a family of matrices, and it looked like from the numerics that the distribution of the normalized eigenvalues was a Gaussian. And some people gave us heuristics as to why it was a Gaussian. It turns out it's not quite a Gaussian. There was a little bit of a defect. And independently at the same time, another group of researchers were looking at the same set of matrices. They also thought it was a Gaussian. And we viewed it differently as to what was the obstruction. We found that if you tweaked the ensemble just a little bit, then that made up for the defects and you got Gaussian behavior. Here, the nice thing about wrapping things around is that each diagonal now has the same length. And so you no longer have the main diagonal of size n and then the corners of just size 1. Everything has size n. So everything basically is on some sense on an equal footing. All right, so we want to understand the distribution of the eigenvalues in something like this. So whenever you have a family, you need some type of averaging formula to make progress. And the question is, what is the smallest family that you can investigate where you can still have an averaging formula available to help you? The larger the family, the easier it's going to be to do the calculation, but the less likely you are to find something interesting. So you want to find the smallest interesting thing possible that you can study. So in my mind, as soon as I see this, I have a dial in my mind. So today it's not just a talk about how complex analysis enters, it's a little bit of a talk of how do you actually do new research. In my mind, I have a dial that controls the amount of the degree of periodicity. How long do I have to go before things repeat? So what are the possible extreme cases you can set the dial at? 0 and n. Well, we can't quite do 0. So 1. So if it's 1, what can you tell me about the matrix? Not every element is the same, but you're close. Every element on a given diagonal is the same, and these are called Toeplitz matrices. And this is actually the ensemble I told you about that was almost periodic. But this is actually more than just a generic Toeplitz matrix. This would be, I believe, approximately a wrapped around Toeplitz. So I think this would actually become a Gaussian. The other extreme is if you make the period n, so the period is actually now depending on the size of the matrix. What kind of matrices do we have now? I'm sorry? Yeah, so everything on the diagonal is different. So what kind of matrices will these be? Okay. General, what kind of n by n matrices? General real symmetric matrices. So you now interpolate between two extremes. When the period is 1, you have essentially Toeplitz matrix or essentially palindromic Toeplitz matrices. And when it's n, you have real symmetric. Well, we know real symmetric is the semicircle. It turns out the modified Toeplitz is going to be a Gaussian, and this is going to give us a nice way of interpolating between the two. In general, it is extremely hard to come up with an ensemble of matrices where you can write down a closed form expression for what the density of eigenvalues will be, for what that probability distribution is. Most distributions are extremely painful to work with. Okay. So let me just try to highlight the calculations and just show you how some of the math that you've been taking in a bunch of classes actually plays a role without getting bogged down into the technical details. If you want to get bogged down into the technical details, you can read the papers that I wrote with William students and small students, or you can ask me. But in terms of just giving a talk, I am operating under the assumption you do not want to go through every algebraic step. You want big picture. So what's going on? We want to calculate, say, the nth moment or the 2nth moment. And so we look at, our matrix, we look at the trace, we're going to weight it by the probability. So that's what the expected value means. The E is the expected value. So it takes the product, multiplies it by the probability we chose that matrix. We know things have to be matched in pairs. And so what we're going to do is we're going to count how many times we have different pairs. And so if we have 2 things together that are matched, that's going to give us a second moment. It's going to give us the moment of that probability distribution, the second moment. If we have 3 things paired together, what's that going to give us? Third moment. If we have 5 things together, it'll be the 5th moment. And so what we care about is how many times in our matchings do we have exactly 5 times 2 things matched, exactly 6 times 3 things matched, and something like that. So you give me a choice, and I will tell you how many times that comes. And so I need to count how many different ways there are, and then see which ones contribute. Now, I've told you by looking at, counting on fingers, the only contribution that will matter is going to be in the case when everything is matched in pairs. There will be no triples, there will be no quadruples, there will be no quintuples. But right now, more generally, I can say, let's just look at some kind of matching. So maybe I have 4 matchings in pairs, 3 matchings in triples, no matching in quadruples, and 1 matching in a quintuple. Maybe I have something like that. And then I figure out what the contribution is, and I weight it by how often it occurs. Okay? And so here's a way of just giving me one contribution of matching things in pairs. So here is the matrix, and I have put in, hopefully easy to see colors, red, green, and blue. Should there be 4 colors? No, 3 colors. Yeah, red, green, and blue, the different matchings. So I have C1 matched with another C1, D2 matched with a D2, and a D3 matched with a D3. And I'm trying to represent this in a way that will make sense, that might be similar to things you've seen before. So where have you seen something like this before? Not everyone has taken this class. I'm sorry? Yeah, from what class? From topology. And so as soon as you see a gluing diagram, what do you want to do? You want to glue it, right? And see what kind of object does this make? And so here I've matched everything in pairs, and things are actually matched in the opposite direction. And this can be seen by the fact that I never have 2 things on the same side of the diagonal. So if I have a C1 in the upper triangular part, it's matched with something on the lower triangular part. Could it have been matched with something in the upper triangular part? Absolutely. But for this particular example, all of the matchings are have 1 on bottom and 1 on the top. It turns out that if you ever have 2 that are on the same side of the main diagonal, it doesn't contribute. The only ones that contribute are when they are on the opposite sides. And so what kind of object is this going to give us? We need to know a little bit of topology here. I'm sorry? Yeah, it's going to give us some kind of torus. These are going to be nice orientable surfaces with some number of holes, because everything is going to be matched nicely that I can glue it together. There's not going to be any of these twists. You're not going to have Klein bottles or anything like that. Okay, those ones are possible, but they don't contribute. The only ones that contribute are the nice orientable surfaces. And so what you can do is you can then figure out, it's missing a little bit on the bottom, unfortunately. You can try to figure out what is going to be the contribution. And if you do the algebra, it turns out that if we have, I think we have 2m vertices. So if you have something that's a genus G surface, it gives a contribution of m to the minus 2g. And again, the actual details don't matter. What matters is that there is a connection now between which terms contribute and topology. So now the question becomes, if I give you a bunch of points, if I give you 2m points on the unit circle, and I match them in pairs, and I put an orientation so I have an orientable surface, how many ways can I get a surface of genus 0, of genus 1, of genus 2, of genus 3? And so you now need to input into your theory these counts. And once you know how many times you have a genus 2 surface, then its contribution is going to be m to the negative 4. How many times you have a genus 3 surface, its contribution is going to be m to the minus 6. And so it turns out that there is a beautiful formula due to Hare and Zagaye that gave a generating function for the number of pairings of a 2K gon giving rise to a genus G surface. When you are doing research, as some of you have already done, and some of you I hope will do this summer, one of the greatest challenges is how much do you prove versus how much do you take on faith and move on? Ideally, you want to prove everything. You don't want to take anything on faith. But if you prove everything, then you have no time to get anything new done, or at least it's going to be several years before you do that. So what things are reasonable to say, I'm going to accept for now that this is true, use this and move on. I have related, I think, the story of the thesis defense at Princeton that failed, where they were using a result in a A-level journal that had been recently published that had a missing condition. And so their thesis collapsed in real time. It was not fun. And so this is the danger of, when you use something where you have not gone through every step. But when you are young, if you go through every step of every paper, you're going to get a solid foundation, but you're not going to be active. And so it's a really delicate balance as to what result is established enough that you can use safely versus do you really want to make sure, especially if you're going to be using it, that I understand exactly why it's true. Whenever possible, you want to put in tests to see, is this result reasonable? If you can ever write numerical code and check something, do so. Simulate it. If you have some combinatorics, put in some special cases and try to compute and see if everything works out. So anything you can do to test. So we have this beautiful formula for the 2kth moment. And we do know formulas for the EGKs. Okay, and so what they proved is that the EGKs satisfy this beautiful relationship. This sum is equal to 2k minus 1 double factorial CKR, where the CKR are the coefficients of the following. So we can write the 2kth moment as this nice product. 2k minus 1 double factorial times these coefficients, CKM. And we have an explicit formula for the 2kth moment. And then the question is, if you know the 2kth moment, do you know the probability distribution? Well, all the odd moments are going to vanish. And so we know the even moments. So can we somehow invert and get the distribution from knowing the moments? So again, the moment generating function was the expected value of e to the tx. When you look at its Taylor series, you get the moments. Now we want to go in the other direction. If I give you the moments, does that uniquely determine the distribution? Not always. We have to be careful. Also, what is another problem with the moment generating function? Convergence. It doesn't always exist. I hate doing this, but I know I'm going to do number theory later, so I will say this. When in doubt, if you need something that doesn't converge in probability, whom should you go to? Who's our go-to distribution? Cauchy, right? 1 over 1 plus x squared. You can argue as to whether or not it has a mean. It does not have a finite variance. It clearly doesn't have finite higher moments either. So unfortunately, we do not always have the moment generating function exist. The characteristic function, which depending on how bad your accent is the Fourier transform, does always exist. And this gives you some sense of why complex analysis plays such a key role in these investigations. It gives you an object you can work with. All right, so what we want to do is we know the moments, and we want to go from knowing the moments to knowing the distribution. So what we're going to do is we're going to look at the characteristic function, which is basically going to be related to knowing the moments. We're going to be using an imaginary argument rather than just a pure real argument so that things converge. Okay, it's amazing how much of a difference this makes. When you look at this expression, do you think that this sum is going to converge? So we have IT to the 2k, the 2kth moment divided by 2k factorial. And just to look at what's going on, the 2kth moment is m to the negative, k plus 1, 2k minus 1 double factorial ckm. Oh, sorry, m is the degree of periodicity. I'm sorry, m is the degree of periodicity, sorry. It's 2k, that's the size of the number of points we're looking at. M is the degree of periodicity. So we have to divide this by k factorial and multiply by t to the k. Do we think this is going to converge? Okay, so let's imagine CKM is nice. What would be a really nice choice for CKM? 1, right? I'm thankful you didn't say the smartass answer, which I would not accept. What would be the smartass answer? 0, right? If CKM is 0, it's clear that it's going to converge. So let's just assume CKM is 1 and see if we can understand and get enough for convergence. So we would have 2k minus 1 double factorial divided by 2k factorial, and we would multiply by t to the k, or t to the 2k. I think it's t to the 2k, t to the 2k. Well, t to the 2k is only growing geometrically. That's not so bad. Can you tell me roughly what is 2k minus 1 double factorial divided by 2k factorial? Roughly, among friends. Do you think they're of similar size? Do you think one is much larger than the other? So it would be 2k double factorial because we've lost all the odds. 2k double factorial, I can pull out a 2 from each factor. That's 2 to the k, and then I have k factorial. Oh, beautiful, right? So if I divide this by 2k factorial on the next page, I would just have, t to the 2k over 2 to the k. Okay, that's not so bad. And I would have a 1 over k factorial. That's great for convergence. So as long as the CKMs are not growing too rapidly, we're in great shape. And so if you look at this, you just have to show that the CKMs are not growing that rapidly, and you have no convergence issues. So it's a nice exercise. Try to get a sense of how large can the CKMs be. All we need is some weak bound because we have a k factorial down below. If you didn't see that 2k minus 1 double factorial over 2k factorial is just 2k double factorial, what you could say is, well, every even is larger than the odd next to it. So 2k minus 1 double factorial has to be less than the square root of 2k factorial.
I have a question.
Yes.
Isn't it supposed to be 1 over 2k double factorial?
Right, so if I divide this by 2k factorial, I get 1 over 2 to the k, 2k double, I'm sorry, I get 1 over 2k double factorial. But 2k double factorial is just the product of the evens. So if I pull out a 2 from each one, I get 2 to the k, and then k factorial. So when I'm looking at the ratio, it's actually going to be something like 1 over 2 to the k, but a 1 over k factorial. And the k factorial grows so rapidly that I'm not worried about the t to the 2k. I just need some weak control over how large the CKs can be. Okay. And so as long as I have some weak control over the CKs, so I'll leave that as a fun extra credit, is looking at this, can you give me a weak enough bound on the CKs, the CKMs, to prove that the sum converges? Once you see a factorial in the denominator, you should be pretty excited, and you shouldn't really be worrying too much about convergence. All we need is a good enough bound to show that we can continue. Okay, so I leave that as an exercise. So now we just plug in what everything is. And so we get 1 over m, the sum of negative t squared over 2m to the k factorial. That's from what we were just talking about a moment ago, times ckm. And now we remember, where were the CKs? The CKs were defined nicely in terms of expressions like this. And so when we put things in, we can actually express things in terms of doing contour integrals. Because we know the CKs form this beautiful relation. If we sum 1 plus 2, the sum of the CK x to the k plus 1, it's 1 plus x over 1 minus x to the r. So when we put that in here, we now have a nice function to the mth power. Can we do an integral like this? Yeah. This is complex analysis. We learn how to do integrals like this all the time. What's the only thing that matters when we're doing this integral? Poles. So where are the poles going to be for this? So when z equals 1, things blow up. What about z equals 0? Yeah, I think z equals 0 is going to be a little bit bad. Now, when we have 1 over 2 to the z inverse, so that's really a z upstairs. But we've still got the 1 over z inverse. So I would look at what's going on at z equals 0. We also, of course, have a dz over z if you look over there to the right. So almost surely, let's be careful at z equals 0. Let's see what's going on there. Let's look at what's going on at z equals 1. Is there any other point we have to worry about? No. We just have to figure out what are the residues at those 2 points. And so when the dust settles, we have the following for the Fourier transform. So this is not the density. We need to somehow invert this. So if we invert this, using some standard techniques, we get an explicit formula. And so if I have a period M, this is my expression. When M equals 1, it's supposed to be a Gaussian, and you can actually see, yeah, it does look like there's a Gaussian there. I see the e to the negative m squared over 2. So it at least matches my intuition that, I've done previous work. When m equals 1 and you're constant along diagonals, this is a Toeplitz ensemble, and previous work on Toeplitz gives you Gaussians in this case. As m goes to infinity, it should become a real symmetric ensemble. You should be getting the semicircle. When you look at this, does this look like this is the semicircle as m goes to infinity? No. So I brought in Professor Strock from physics. He has a lot of experience looking at some special functions, and we played some games, and it's a beautiful, beautiful topic, trying to understand special functions and what does this converge to. And with work, you can show that this does converge to a semicircle. It's not at all clear when you look at this that this is a semicircle, but boy, is it helpful when you do the analysis that you have a belief that it should be converging to a semicircle. That helps guide you in what you're doing. Yes? Sure, as m grows, this density is going to look more and more like a semicircle. So when m equals 1, we'll see it in a moment, it's going to look like a Gaussian. And as m gets larger and larger and larger, it's going to look more and more like a semicircle. But for any finite m, it is going to have infinite support. So it is going to be interesting. So this is the case when m equals 1. And I am plotting a histogram of the eigenvalues of 100 of these circulant matrices of size 400 by 400 against a Gaussian. So this is a complex analysis class. This is not a statistics class. Is this convincing to you? Yes. On the theoretical side, this is convincing enough. Let's look at m equals 2. And again, when we plot the histogram, it does a wonderful job of fitting what is going on. And we do see a beautiful matching of the two bumps. When we take m equals 3, again, it looks pretty good. Is the fit getting a little bit worse? I think it's getting a little bit worse. M equals 4, m equals 8. Does this look like a semicircle? It's getting there. It's definitely looking a lot more semicircular than the beginning. It still has unbounded support, but the decay is so rapid that for all practical purposes, it has essentially bounded support. Now, when you do certain calculations, because there is probability arbitrarily large, that can cause some issues. But when you're looking at this, almost all of the probability is essentially between a little bit more than -2 to 2. All right, and then this is looking at 20. Again, looking closer and closer and closer to a semicircle. And then just putting them all together, and by plotting it like this, you can see the pinching coming in of the probability of getting further and further out. And then I think, yes, and you can see in the limit the solid semicircle with everything fluctuating about it. And you can see it is really getting very tight around the semicircle. And this is already just looking at m equals 20. So the convergence is setting in fairly quickly. And in problems like this, you always want to get some sense of how long do you have to wait before you start to see convergence. So this was one of the more interesting projects we've looked at over the years. Yes.
Do you have some sort of relation between the length of your diagonal period and the size of the matrix? Like some sort of ratio?
So what we're doing here is we're doing fixed period, independent of the size of the matrix. If the period grew with the matrix, then the behavior would set in extremely rapidly as n goes to infinity.
So at 20, it is reasonable for 100 by 100.
Yes. Let me see what size matrices. We're using 400 by 400 matrices.
So then
So 20 would be 20 over 400 is the same as 2 over 40 or 1 over 20 or about 5%. And so, yes, I mean, as it gets very, very large, if you're at 20, you're going to see behavior very similar to this. Because these are the limiting over here. This is the limiting plots over here. Over here, these are the numerics. And so the limiting plots, you can see the behavior has set in extremely quickly. Have I proved in this class that there are infinitely many twin primes? In fact, that 20% of all numbers start a twin prime pair and 40% of all integers are prime? All right, I will prove that now. So can somebody give me all the primes up to 10? Shouldn't take that long, come on. 2, 3, 5, 7, 40% of integers are prime. And which primes start a twin prime pair? 3 and 5. So 20% of all integers start a twin prime pair, 40% of all integers are prime. If you don't believe that this pattern persists, let's double the range of investigation and count all the primes up to 20. Can somebody give me the primes from 10 to 20? 11, 13, 17, 19. Again, 40% of integers are prime and 20% of integers start a twin prime pair. The numerics are quite misleading. Why are the numerics so misleading? Because the primes, they converge on a scale of log. It's very slow to see what's going on. The number of primes up to x is x over log x. The density is slowly decreasing. You have to go quite far out before you really see the correct limiting behavior. So when we are looking at various things, for small values, it can be extremely hard to tell the difference between some behavior that's growing like x to the 1/2, or maybe x over log x, because you're going to have different constants in front, and it's going to be very hard to see the limiting behavior. So the question of, how should m be relative to n? Well, here I have m is fixed and n is going to infinity, but I could look at it as m is just 5% of n, and it's a constant percentage. So for small values, it's very hard to tell the difference between some number of powers of logarithms, some powers and whatnot. They all look roughly the same in small regimes. And it is very easy to be misled by data. I've done a lot of work on elliptic curves. The key thing that matters is the log of the conductor. And so if the conductor is of size 10 to the 15, which is a good size number, what's the log of 10 to the 15 approximately? Around 30. You would never make extrapolations about primes from looking at the first 30 numbers, or at least you shouldn't. But a lot of people, when they saw data for elliptic curves and they saw billions and trillions of examples, people thought, well, we have so many examples that these patterns probably persist. Well, the problem is these patterns are all coming from elliptic curves whose conductors, say, of size 10 to the 15, on a log scale, which is the correct scale to study, this is around 30. This is not far enough to really be seeing the limiting behavior, and it's very easy to be misled. So when you are trying to do these investigations, the real challenge is to figure out what is the correct scale to study things. And unfortunately, when you try to do the numerics, frequently we can't go far enough to see what's going on. So there's some slides I have when I present families of elliptic curves where I have about, I think, 15 data points. And you can see a little bit of difference between the small 15 data points and the next largest set of 15 data points. And it's like, But it wasn't for a long time before one of my colleagues actually went far enough in one of these families to really see the limiting behavior kick in because of just how long it takes. All right. Just some other ensembles, so there's so many different ensembles that you can look at. Anybody know why we chose W? I'm sorry? Wigner is a good choice, but not Wigner. I'm sorry? Not Weierstrass.
Koshi.
Nope.
Riemann.
Nope. Thank you for balancing. Would it help if it was in a different color other than red? Yeah. Oh, no, it's for weight. So a lot of times what you do is if there's something that you want to do, you can choose a different word or whatnot, and then that can be the word that you officially use, but there could be enough. So I think Borel sets, I've heard, there were originally sets of type A and then sets of type B, and the sets of type B are the ones that were useful. I've never bothered to check to see if that story is true because I just love it as just a way to try to get the name as you want. But think about how you want to name things. So we were looking at checkerboard matrices. So every so many spots, we always put in the same value. And then the question is, when you have this increased structure, what can you say about the distribution of the eigenvalues? And what we saw here is, for the first time ever, we actually saw a split in the probabilities. Almost all the eigenvalues were in the central band between minus root n and root n, up to a little constant. And there were a small number that were a little bit larger. And the number that were larger was exactly equal to how many spaces I have to go before I get the next W. So if W was 3, there would be 3 of them. And if you look at what happens as you go larger and larger and larger for the size of the matrix, you can see that little blip keeps moving further and further to the right. Oops, uh-oh. And so it just keeps moving further and further to the right. So almost all the eigenvalues are concentrated in the central band. And almost all the eigenvalues have size on the order of square root of n. A small number of eigenvalues have size n. The number of eigenvalues is equal to k, which is fixed. So as n goes to infinity, do you think those 3 eigenvalues matter that much? If k equals 3? If n minus 3 of the eigenvalues live in this big bulk, and there's 3 large eigenvalues, can they really cause much damage? No, but in terms of how the method works, they completely destroy the method. Because we want to calculate the moments. Let's calculate what the moments are from these. These are of size square root of n. So if you want to look at the 2mth moment, and you have something of size square root of n, you raise it to the 2mth power. That gives you n to the m. We have about n of them, so that gives you n times n to the m, or n to the m plus 1. Okay? So the contribution to the 2mth moment from almost all the eigenvalues is going to be of size n to the m plus 1. We have 3 eigenvalues of size n. We raise it to the 2mth power, that's going to be a contribution of size n to the 2m. So those few eigenvalues over there completely overwhelm the eigenvalues in the bulk. Even though there's only 3 of them, even though there's a bounded number of them independent of n, they completely outweigh and destroy the method of moments. And so we had to use some interesting tools to focus on the 2 regimes one at a time. There are complex generalizations you can do. It's trying to do, what kind of interesting shapes can we make? Lots of interesting pictures you can do. All right. I was trying to either do Saturn or the CBS logo. I forget what we were trying to do here precisely. But you can basically come up with like rings of eigenvalues now that are separated. And so it becomes an interesting question, how can you generalize these results? So what I want to end with is just a quick introduction to L functions. And so we've talked a lot about this before, but it's important to remember because so much of complex analysis was developed by the search for understanding how many primes there are up to a given height. And then the generalizations of that has been driving the subject for over 100 years. So some of these slides should look familiar. We have the Riemann zeta function, and this makes up for having that bad distribution earlier. So it's defined as the sum of 1 over n to the s, where n ranges over the integers. By unique factorization, it's the same as the product over primes. And the hope is by understanding the integers, we can use that to deduce information about the primes. We talked about some special value proofs. If you take the limit as s goes to 1, you have 1 over n, which is the harmonic series which diverges. So that gives you there must be infinitely many primes. The other one I like is if you take 2, you get the Basel problem. The sum of 1 over n squared is pi squared over 6. Because pi squared over 6 is irrational, there must be infinitely many primes. Otherwise, the product would be, if the product was finite, it would have to be rational. So we talked about the functional equation and analytic continuation, extending it to being defined over the entire complex plane. It has a simple pole of residue 1 at 1. And the Riemann hypothesis is that all of the non-trivial zeros have real part 1/2, so that you can write the zeros as 1/2 plus I gamma. What that means is there is a natural spacing between the zeros. You can talk about the first zero, the second zero, the third zero, the fourth zero. This is similar to the energy levels of heavy nuclei. This is similar to spacings between events. And so the idea is we can start asking questions about what can you say about the gaps between the zeros? And it turns out that so many problems in number theory are related to gaps between zeros. How many people here have seen the class number? Maybe an algebraic number theory. So bounds on the class number are actually related to the zeta function having a lot of zeros close relative to the average spacetime. It is amazing how many problems are tied up into stuff like this. And the observation, which I mentioned before from Montgomery when he was talking with Dyson, is that it seems like the spacings between zeros are similar to the spacings between complex Hermitian matrices. These are Hermitian matrices where we're choosing the entries from Gaussian distributions. I don't want to go into all the detail about the subject. The main idea is that if I give you a matrix and I write it down, I have to choose a coordinate system. Physics, to our best understanding, and we have a couple of people here who can correct me if I'm wrong, does not care how we orient our coordinate axes, right? The laws of physics should not change because of what direction I call north, what direction I call east. And so when I give you a matrix, what really matters are the eigenvalues. The actual matrix elements coming from how I choose to write it down doesn't matter. So if I give you a matrix, let me diagonalize the matrix. So I now have a diagonal matrix and I have a unitary transformation that, through conjugation, U Hermitian A U converts me to a diagonal matrix. And the diagonal matrix is the one where the physics is contained. The unitary matrix is just how I should orient my coordinate axes so that it looks nice. And that's why I really only have n objects that I care about, the eigenvalues. I don't care about the other matrix elements so much. And so for a while, physicists were looking at choosing matrices by choosing matrix elements at random. And you wanted to choose your distribution of your matrix elements so that if you did an orthogonal change of variables, it would not change your probabilities. And that led to differential equations. And when you solve the differential equations, it forced the matrix elements to be chosen from Gaussian distributions. And that's why it's called the Gaussian unitary ensemble, is you get Gaussians when you assume that the probability is invariant under unitary changes of variables because physics should be the same. Now we just use unitary matrices and how measured, but this is where it's coming from. Instead of studying this classical zeta function that avoids, I think, another count, we can study more general L functions where instead of having a 1 everywhere, we have some coefficients AF of n. You can study anything you want. The question is, when is it going to be useful? And for the most part, if there's not an Euler product, it's not considered useful. There are generalizations of the Riemann zeta function that do not satisfy the Riemann hypothesis, but none of them have an Euler product. So we believe the Euler product is absolutely fundamental to the key properties of the object. And again, we believe that the generalized hypothesis holds that if you appropriately normalize things, everything has real part in 1/2. If you've ever worked with elliptic curves are sometimes normalized so s goes into 2 minus s rather than s goes into 1 minus s, just because that way certain things become integers. Most people normalize everything now so that everything is s goes into 1 minus s. And so, for instance, if I wanted to look at an elliptic curve, how many of you have seen a picture like this before for elliptic curves? Okay, good number of you have. So if you haven't seen it, this is one of the most beautiful connections between geometry, algebra, and number theory. So an elliptic curve is something of the form y squared is x cubed plus ax plus b. Let's say a and b are rational numbers. If I take 2 points on the elliptic curve, p and q with rational coordinates, and I draw the line connecting them, it's going to hit the elliptic curve in another point, which I'll call r. If I take the same point twice, I'm basically getting a tangent line. And it turns out we can define a group law of addition, and we define p plus q not to be r, but the reflected point underneath it. And we'll call that point p plus q. And when you do that, it turns out you have a abelian group on the set of rational solutions. If you think about it, if a and b are rational numbers and p and q have rational coordinates, if you draw the straight line connecting p and q, y equals alpha x plus beta, alpha and beta have to be rational because we're going through 2 rational points. If you then replace y with alpha x plus beta, and square it, you've now got a cubic where all the coefficients are rational. So you have a cubic with all the coefficients are rational, and it has two roots. One is when x is equal to px. One is when x is equal to qx. So the third root has to be rational, or when you multiply everything out, you wouldn't get a rational polynomial. So it's a nice exercise. Prove that if two roots of a cubic with rational coordinates, rational coefficients are rational, then the third root has to be rational as well. So that you have this nice closure. If you start off with two rational points, you end up with a rational point. I am not saying what the point, the zero element of the group is. It is the point at infinity. There is a way to make sense of what that is. And it turns out that there's a structure to this group, and it's equal to some number of copies of the integer z plus some finite torsion part. And you can build an L function. And for the L function, I'm going to just say what's going on at the prime. At the prime, the coefficient is going to be the number of solutions, mod p, and I'm going to subtract that from p. Well, if you think about what's going on, if I look at y squared as x cubed plus ax plus b mod p, half of the time, a given number is going to be a perfect square mod p. Half the time, it's not going to be a perfect square. Well, what do I have to be careful about? What number? So if you're a square, typically you have two square roots, except for what number? 0. So on average, if I give you a generic number, you would expect there to be one root. So if I count as I vary x, if I count how many times do I get a y that works, I would expect on average for each x, I get 1. Sometimes it's 0, sometimes it's 2, sometimes it's 1. And so I expect this sum to be of size p. And so this is a really common thing we do in mathematics. If you have a belief of what the main term should be, start off with that. And then subtract off and try to look at what's going on beyond that. Try to look at the fluctuations. And so I get p minus the number of solutions. And it turns out when you look at this L function, this is one of the $7 million problems from the Clay Math Institute. If you solve this, not only do you get an A in this class, but I will retroactively, I will retroactively go forward and fix all the classes that you've already taken, as well as arrange for you to get a PhD from your institution of choice, as well as win whatever math prizes you wish. You're all young enough that you're not age limited. So anything you want is on the table. The famous Birch-Swinnerton-Dyer conjecture says, if you look at this L function, and you look at what is the order of vanishing of this L function at the central point, which in our normalization is s equals 1/2, although it might actually be s equals 1 the way I've written things, that is equal to the number of copies of z in the geometric rank. And so complex analysis is looking throughout so many of these calculations. I'm not going to go through all different places. Have I shown you these slides earlier when we did the Riemann zeta function? Did we do this? Did we do these slides here? Well, let's just quickly do them. So whenever you have a function complex analysis, one of your go-tos is going to be doing a contour integral. And in particular, do a logarithmic derivative and then do a contour integral. So let's look at zeta prime over zeta. That's really taking the derivative of log of zeta. And because we have the Euler product, the log of a product is the sum of the logs. So when we take the derivative of the product, we have the derivative of the sum of the logs. The derivative of the log is easy to do, and then we use the geometric series to expand the bottom. And it turns out when you do the expansion, the only thing that really matters is the first term in the geometric series. Everything else is going to be easy to control. And now when we do our contour integral, if we calculate things on the right-hand side, as we shift contours, it picks up contributions from the zeros and poles of the zeta function. And on the right-hand side, we have a detective function. And when you do that contour integral, it turns out it's 1 if p is less than x, 0 if p is greater than x, and what would you guess it is if p equals x? 1/2, right? So just make sure to be safe that x is not a prime, and you're in good shape. And so this just says that the sum of log p is related to a sum over the zeros and poles of the zeta function. There's only one pole, and that's going to give you a contribution when s equals 1. That's going to give you an x to the first power over 1, Because it's a pole, I get a negative sign, so I get an X from that. All the zeros, I'm going to get, if the Riemann hypothesis is true, a 1/2 plus I gamma. That's going to give me something of size X to the 1/2, much smaller. And that's the famous hypothesis. And that's why it matters so much. It gives us counts. What we can do instead is we can look at putting in a test function phi. And if we put in a test function phi and we do this calculation, we now get information about what's going on through the zeros by looking at phi. So the last slide I wanted to just quickly mention is just the physics connections. So in physics, we study energy levels. In number theory, we study zeros of L functions. In physics, we shoot in neutrons and we see what comes out. In number theory, we shoot in Schwartz test functions, functions of rapid decay. In physics, we can only shoot in neutrons of a given energy band. In number theory, we can only calculate the sums that arise if the test function has suitable support. So complex analysis is an absolutely fundamental tool for studying problems like this. All right, so this is a good place to stop for today. The next class will be another application.